All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207, the last edition. Still have some people trickling in here. Let's get things set up. So, I guess some announcements before we begin. So obviously, you know that the test is today. So the practice test wrapped up at 3 p.m. today. The answers were actually sent out to everyone at 2 p.m. So hopefully you guys got that email. And homework has been extended to Saturday. So I was getting some questions on homework. So yeah, today is going to be our last lecture. I probably won't use up all the time, so I'll have plenty of time for questions at the end. Homework is extended. The test needs to be done by 9 p.m. tomorrow. And more people in. Final is on Monday. So we'll have the final during regular scheduled class time. So no lecture on Monday, but we'll have the final on Monday at that time. I'll send you guys more information on that via email, what to expect. Other than that, if there are no questions, I guess we can jump in and let's finish the last topic. So there we go. So this is what we did yesterday, which we're focusing on volumes, particularly volumes of revolution. And we saw the general concept that we can think of volume as the integral of cross-sectional area. And when you have a volume of revolution, the cross-sectional area is actually a circle. So we can use the pi r squared idea to find the integral of volume. That led us directly to something that we call the disk method because it looks like a disk when you look at it sideways. And we looked at applying that formula, the idea of an inner radius and outer radius, and what we need to do. And we did a bunch of examples. So I guess we don't have to go too much in detail about that because we did a lot of them. We also looked at something else called the shell method. And the formula there was the integral of 2 pi rh, where r and h are distances and they're measured with right minus left or top minus bottom. And we looked at how to actually do that. And we did a bunch of examples. We also looked at the fact that it is possible that one method could be more efficient or better to use than the other one, depending on the particulars of the problem. So you should know how to find each component that you need for each method and be able to look at a picture and tell, oh, there'd be an issue here if I used the disk method versus the shell method or vice versa. So that is something that you have to worry about. And we looked at an example here where on the same example, just me asking you to go around a vertical line versus a horizontal line, it affected with which method worked better. So for this one, the shell method worked better because we had multiple types of inner and outer radii. And for this one, the disk method worked better because our height function would not change. And yeah, after that, we had some Q&A, which not everyone was there for, but it really applied to the second test. So I guess you guys can watch the videos there. But this brings us to our last lecture, lecture 19. So this is going to wrap up the syllabus. It's also going to give you the last bit of information you need for the last few homework problems. So there are a few homework problems on this. I don't know, 2 or 3 of them, something like that. So now we're going to know how to do those. So the idea here is to find the area of a surface of revolution. So the main info is here, the important formulas. You see it's right there. Looks kind of complicated. We're actually going to talk about that. But let's say f is a positive continuously differentiable function, and we're going to rotate that function around the x-axis. You'll actually create the skin of some sort of solid figure. And the goal is to find the surface area of that 2D object. And it turns out that this is the formula. So S stands for surface area. And the way we would find that surface area is this particular integral. So it's another applications of integral as you can think about it. So it's going to be 2 pi times the function f squared times the radical of 1 plus dy dx squared time dx. And if that component looks familiar to you, that's because that's the arc length component of an integral. We know that if we only integrated this part only, that actually gave you the length of the curve. You might actually notice that. We can also have the curve in a different variable. So instead of being given as y equals f of x, we can be given it as x equals some g of y. And the formula will change accordingly. It will become dy dx dy all squared. But essentially you do the same thing. And so before we jump into it, I'd actually like to talk about, well, why is this the case? Where do these formulas actually come from? So let's say we have a curve here. This is our f of x. Say y equals f of x in the plane. So this is your y, this is your x. And let's say I wanted to rotate this around the x-axis. So you can imagine this will rotate, come some sort of disk. This will rotate here, come some sort of disk. Right? It's supposed to be symmetric. I don't know why it looks like that. Looks a little better, right? And so you rotate it and you create this, like, looks like a vase sideways, right? And we actually want to find the surface area of this object that we just created, okay? So how we can do that, so this is, we create this object here. So how we can do that is we can actually go in and we can just look at one band at a time. So let's say I slice off a band of this object right here. Again, it's calculus, so it's an infinitesimal slice. So this band is very, very super thin. And we can look at, say, the radius of that band, which is just measuring up to the function, which is y. And then it's just a band around that thing. And essentially, we look at things one band at a time. So we're taking a very calculus idea, just slicing things up into little pieces, figuring out what happens to that little piece, knowing that the answer will be the sum of all these little pieces, and then we can get an integral in there. So if you just look at this band, you'll just have this part right here. Right? And then what we can do is we can actually unravel this band. So now we have this little, it won't be an exact rectangle, it'll be a little bendy rectangle, but things are so thin that the bend is barely perceptible. And so we're going to kind of treat it like a rectangle in our approximation. And of course, when we use an infinite number of these, it actually won't matter. It'll be approximated by a rectangle. So if we look at the length of this rectangle here, notice that that comes from this length over here. And so that's essentially like the circumference. So here, the radius is like the height of the function, which is y. And so this length here is going to be 2 pi times y. If we look at the thickness here, this we will call delta S. Now, S is just a standard notation. S is like the arc length. Standard notation. So lowercase s is another, I know we called it big L in all my formulas, but more standard is the little letter s. And so this is just a slight change in s. So the entire length here will have length s. And I just took a little part of that, which is just a little bit of s, a little bit of delta s, whereas the length of the whole thing is s. Okay. And so now, so here delta s is a small change in s. Or just one of these dissections. And so essentially, now we end up with this idea. We can find the surface area. That actually didn't look much nicer. The surface area which we will denote big S for surface area, we can approximate it by adding up all of these bands. So we're going to add up a bunch of things that all look like this, delta S. And so this means that our S is going to be equal to just take the limit as n approaches infinity of those things. So we're slicing this into n things. I'm not specifying that, but we kind of know this game already. And so this actually becomes an integral, say from a to b, because our function is going from a to b. And we have 2 pi y, and delta s becomes ds. But remember, ds is just another name for the arc length differential. So this is really, we have that formula for arc length for a function of x. It's essentially 1 plus dy dx all squared dx. And so that's sort of where this formula comes from. Now, as I sort of suggested, just bringing things back to more standard notation, this thing, the arc length part, this is commonly referred to as ds. So that is be what the delta, the change in arc length differential looks like. So you can actually think of ds as this expression. Depending on whether you're given your curve as a function of y equals f of x, then your ds will be 1 plus the derivative of that all squared radical. Or if you're given x equals some function of y, then the derivative with respect to y of that guy, if we put it in that same formula, ds can also be thought of in that way. They both will be using the same derivation to come up with the arc length of that curve. And so that's where these formulas came from. And we can kind of summarize here. So the same idea would have happened if I were going around the y-axis. Instead, the horizontal length would be x. And so x would take the place of y here. And so we can kind of summarize all of this in the following way, right? So if I want to find the surface area and I'm rotating about the x-axis, the general formula is going to be the integral of 2 pi y ds, where your ds can be taken on one of two forms depending on how you're looking at the curve. If you're looking at the curve as a function of s, of a function of x, then the ds will take on this form. And in this case, because you're doing with respect to x, you're going to have to replace your y with this expression as x, so you integrate along the x's. Or it could be this form, in which case you just leave y as is, leave it as the variable y, and you integrate with respect to y. Similarly, if we're going around the y-axis, where we had y before, we would now have x. And similarly, your ds can take on one of two forms, where if we want to look at things in terms of the function y, we'd have to replace x with its definition as a function of y. And so we have that. So this kind of summarizes how we would find the surface area of revolution of a curve. Whereas on the left, we're given the curve as like y equals f of x, and we want to rotate around the x-axis. On the right, we're given the curve as like x equals f of y, and we want to rotate around the y-axis. But you can actually do the way the function is defined can be swapped in either definition, and you just change the ds accordingly. So that's pretty much all the theory there and where the formulas come from. Let's actually do some examples. So let's say we need to find the exact area of the following surfaces of revolution. So I have two examples here that I want to go through. But we're going to be using these formulas right here. So I guess you can pause, you can like take a screenshot of that or whatever, but because we're going to be using it. So yeah. All right, awesome. So now this is just an application, which means once you understand the formula, you don't have to rederive it every time. You just apply the formula. You know that there's a formula for finding the surface area given certain information. Here, notice that our function y is written as a function of x. and we're going around the x-axis. So that sort of tells us which formula we want to use. We want to use that one in the left column. So I can say, so using s equals, we're going to do the integral from a to b of 2 pi y times the radical of 1 plus dy dx squared dx. Because my y is given as a function of x, that's going to be how I want to do it. So this would mean the integral is going from 3 to 5. It's 2 pi. I know I have to do it dx, which means my integral has to be, everything has to be in terms of x. So the variable y I can't use, but y is defined as the radical of 5 minus x, so I'm going to plug that in here. Right, so this is the y here. So I need to keep everything in terms of x because I'm using the dx formula. And now I'm going to take 1 plus the derivative of that guy, and I'm going to square it. So this is going to be minus 1 over 2 times the radical. That's me using the chain rule. And dx. So that's that. So now it just comes down to actually computing this integral, which I don't have as many examples today, so I can actually go through the motions of actually doing the integral for you fully. It's not like yesterday where we did like 16 integrals. Didn't have time to go through all of them in detail. Just kind of set it up and tell you this should be the answer. But we'll actually do these today. I think I have 4 examples total, maybe 5, but one of them is like just an interesting idea kind of thing. All right, so let's actually go through this just to remind ourselves how integrals work, because it's going to be important for the final. Let's see here. Let's simplify this a little bit. So I can put the whole thing under the radical. So there's a 5 minus x here, and then a 1 plus, if I square this, it's going to be 1 over 4 times 5 minus x. So I'm taking the second method of integration, the art of integration, where I kind of try to simplify first. Now, if I multiply this out, I would get 5 minus x plus, multiplying that out, the 5 minus x's would cancel. I'd only be left with a quarter here. Yeah. 3, 5, 2 pi. So I can take the 5, add the quarter. 5 is 20 over 4. So this would be 21 over 4 minus x. And now what I can do is I can just integrate that. Now, obviously, there'd be a substitution here. U equals 21 minus 21 over 4 minus x. The du is going to be minus dx, all that. So we know that this is going to be 2 pi times, so this is going to be 21 over 4 minus x times a negative from the negative du. And we're adding 1 to the power, 3/2, dividing by the new power, 2/3. We're going to do that. And we apply the fundamental theorem of calculus. So this would be 4 pi over 3. And if I plug in x equals 5, someone's trying to get in here. If I plug in x equals 5, this would be 21 over 4 minus 5. And that'll be 3 over 2 minus, if I plug in 3, be 21 over 4 minus 3 to the 3 over 2. So this would be minus 4 pi over 3. 5 is 20 over 4, so 21 over 4 minus 20 over 4 is just 1 over 4 to the 3/2. So I'm taking the square root of 4, which is 2, and then I cube that. So this actually works out to 1/8 here. And 3 is 12 over 4, 21 minus 12 That's going to be 9/4. Take the square root of that. I get 3/2. Cube it. I get 27/8. Right? Someone's trying to get in here. So this will be -4/3. Going to combine these. So this is -26/8. So I can take 4 into 8 goes 2 times, 2 into this goes 13 times. And so this would be 13π/3 square units. Whatever that is. Okay. So that's our example for the first one. Right. So given y equals f of x, you have limits on x. You're going around the x-axis. We're using this formula right here. Because I'm giving y equal as a function of x and I'm giving the limits on the x, I would probably go with the dx version of the formula, which means I have to change my y to a function of x and then take the derivative of that, plug into the dy dx part, and then integrate that with respect to x. And this will be what we get. So I have another example here. This time I'm given x as a function of y and given the limits on the y. So I'm obviously going to use the other version of the formula. I just wanted you to see how that would work. So we're still going around the x-axis. So the radius part of our function is still y. It's still the height of the function as a function of y. So we're still going to be using s equals the integral from a to b of 2πy times ds. But in this case, my ds is going to be 1 plus the derivative of x with respect to y squared dy. Right? So my curve is given in terms of y, my limits are in terms of y, so this is how I would do it. Now the difference here is because I'm integrating with respect to y, I'm not going to change this y to another function. I'm just going to leave it as y, right? Of course, that y is going to correspond to whatever y gets this to work, but the integral will already have that built in. I don't have to worry about that because I already have that dx dy inside here. So this would mean that s would be the integral from 1 to 2 of 2πy times this. Taking the derivative of that, I would get 4y squared. And so now we have to integrate this, right? So that's going to be like 16y squared. So that's what we get. Now we're going to have to figure out a way to integrate this. And how do we integrate this? Give me a suggestion. Anyone? Right, a substitution can work here. So u equals 1 plus 16y squared. I'd actually like to do it a little bit variation on that. How about u squared equals 1 plus 16y squared, just to get rid of that radical. Don't really like it. So this would mean that 2u du is going to be 32y dy. I do want to change this to that. So what I can do is I can multiply both sides by, say, pi over 16. So this would mean pi over 8 u du is going to replace the 2 pi y dy. So I get to replace all of this here, 2 pi y dy. This is pi over 8 u du. And then I also get to replace this entire thing with u. And just because I'll change the limits here, when y equals 1, our u would be, well, radical 17. And when y equals 2, our u would be 4 times 16. I think that's 64. So that's 65, rad 65. So this implies our s would be actually equal to the integral of rad 17 up to rad 65 of pi over 8u, and that replaces pi over 8u du replaces the blue part, and then u replaces the green part. So I pretty much just have radical 17, radical 65 of pi over 8 u squared. So I can do u cubed over 3. It's going to be the integral there. So this is going to be pi over 24 u cubed. It's going to be pi over 24 times 65 to the 3 halves minus 17 to the 3 halves. That's that one. Okay, so I mean, the new concept that we're learning is just this formula. And so applying that formula, you just need to understand when to plug in which pieces. And it all comes down to the description. If you're given x as a function of y and you know the limits of y, you would tend to want to use this part as the last part. If you're going around the x-axis, you should multiply by y here. If you're going around the y-axis, you should multiply by x there. And that's pretty much the entire concept. After that, it's just an exercise in integration, which at this point, if we weren't experts by the time we had test 1, we better be experts now. So yeah, someone else is trying to get in here. All right, so yeah, that's this one. Now, just want to take a slight detour to show you something kind of cool. An interesting phenomenon or whatever. This is actually a well-known mathematical object. It's called Gabriel's horn, because it looks like, you know, you can imagine like an angel here blowing the horn. It looks like this, right? Okay, so this is the function y equals 1 over x for x greater than or equal to 1 rotated about the x-axis, right? You'll actually create this kind of object. Okay, and it has some interesting properties. So I'm going to find the volume and surface area for you, because now we know how to find volume and surface area of something that's rotated. So let's actually find the volume. Now we're rotating about something around the x-axis, and we can just look at this as a radius r, and we can actually apply the disk method. So by the disk method, we know we can get the volume by, you know, the integral from a to b of pi times r squared dx. So here, this is the integral from 1 to infinity, because it actually never ends. And it's pi times the radius, which is just the height of the function, squared. So turns out we know how to actually compute something like that. This is the limit as n approaches infinity of 1 up to n pi times 1 over x squared dx. If you integrate 1 over x squared, add 1 to the power, divide by the new power, that's minus pi over x between 1 and n. This is going to be minus 1 over n plus pi. And obviously this will go off to 0. And so this just actually gives you pi. The volume is pi cubic units. Right, so that's something interesting. Okay, so that's Gabriel's horn. And it has a volume of pi cubic units. So you just take the object, take the curve 1 over x squared greater than 1, rotate it around the x-axis. You will create an object whose volume, which means if you fill it with something, how much of that stuff would be there, pi cubic units of that stuff would be there, depending on the scale of your x-axis, right? Okay, what about the area? Okay, so we just learned about surface area, so we can actually apply that here. So we're using surface area equals the integral from a to b of 2 pi y, because we're going around the x-axis, times 1 plus dy dx squared dx. So this would mean our s is equal to integral from 1 to infinity of 2 pi times y times the radical of 1 plus, the derivative of that is minus 1 over x squared dx. This is an improper integral, so limit as n approaches infinity, 1 to the n, 2 pi 1 over x times the radical of 1 plus 1 over x to the 4th dx. Now, it turns out this integral is actually pretty annoying to do directly. Let's see. Yeah, like I wouldn't even try to do this, but there's something that you can notice here is that this guy here is greater than 1 for sure, right? So in other words, you're taking 2 pi times 1 over x and you're multiplying it by something bigger than 1. So it turns out that this integral is actually greater than or equal to if I just ignored that part. Now this one is just 2 pi times ln of x. So it's 2 pi times ln of n minus 2 pi times ln of 1. We know that this is going to go to 0 and this goes to infinity. So turns out that this is infinity. And this is actually a smaller integral than the original one we're considering. So the original one also diverges. So S diverges to infinity by comparison. In other words, It's a very interesting thing. Gabriel's horn has space, not much, has finite volume, but infinite surface area. Which is a very interesting property to have, you know, which means you can fill it with paint, but you can't paint the outside of it. Strange things happen at infinity. So that's just a nice little mathematical, I don't know if you'd call it a paradox or something like that. I mean, you can just see, oh, the math just, this is how reality is. I don't know. Like if such an object could exist, it would have finite volume and infinite surface area, which is a very interesting thing to think about. Like the area of your skin is much larger than the amount of stuff that can fit inside. Very interesting. Yeah, so that was just a cute little example that we can do with the knowledge that we have so far. One little problem where we can talk about volumes of revolution and surface area of revolution all in one thing. But let's actually continue to another situation that we need to talk about. What if we have the curves given in parametric form? Now, we know that this component, the ds component, right? This guy, it's the same component that gives us arc length in the scalar situation. So the exact same argument that I gave above is going to work in the parametric situation, except the notation would obviously have to evolve to cover that situation. And we actually know what ds, or the arc length component, is in the parametric version. In fact, this was the version that I had derived first, and then from this I derived the other one. But here I'm presenting it in opposite order. You can go in either order. But the idea is this is the equivalent version of ds in the parametric form. And so nothing else really changes. If you have a smooth parametric curve, smooth pretty much just means you can take the derivative at any point. In higher dimensions, 3 dimensions and higher, you're going to also want to say that the derivative cannot be 0. And that's because the 0 vector in higher dimensions, which is how you're going to think about things, is a very weird vector to actually do. Like if you get the derivative is the 0 vector, it doesn't mean anything. So, but for us, we're just thinking of something that we can differentiate everywhere. It's continuously differentiable. We call that smooth, because there's a derivative in the formula. So if we have a differentiable parametric curve, x equals x of t, y equals y of t, for some t equals a to b, we only traverse once as t goes from a to b, then we can find the surface here in a very similar fashion. To go around the x-axis, it's the integral of 2 pi y ds. And to go around the y-axis, it's the integral of 2 pi x ds. Our ds in this case, in both cases, is going to be the arc length component of an integral. And in both cases, we would replace our functions with their corresponding functions in terms of t. So y gets replaced with its formula in terms of t, x gets replaced with its formula in terms of t, and so you integrate with respect to t. Conceptually, I don't have to rederive anything because you derive it in the scalar world. It's just a matter of translation to move it to the parametric world. We could have done it the other way around, derived it in the parametric world and then translated to the scalar world. Either way, this is the shortcut. At the end of the day, this is what you need to know. I kind of wrote them out in a little bit more detail here, but it's going to be essentially the same. So now I'm going to do some examples in the parametric version. So let's say I wanted to find the area of revolution of this parametric curve. my x is equal to t cubed and my y is equal to t squared, and I'm restricting my t going from 0 to 1. I want to find the surface area of revolution. So yeah, we're just gonna kind of jump in and use this formula. So using the arc length is going to be equal to, we're going on the x-axis. So it's 2 pi y times the dx dt squared plus the dy dt squared dt. So this means s is going to be equal to integral from 0 to 1. 2 pi times my y is actually t squared. The x dt is 3t squared. I'm going to square that, so I get 9t to the 4th. And my dy dt is 2t, so if I square that, I get 4t squared. So now I actually want to look at what I can do here is I can factor out a t squared from underneath. T is going from 0 to 1, so no, everyone's going to be positive here. Components are positive. So no need to worry about absolute values. Right, normally when you take the square root of something square, it's the absolute value of that thing. So I'm going to want to factor out a common t squared from under the radical, pull it out as a radical of t squared, but I don't need to write absolute value of t because my t is between 0 and 1. The absolute value of t is the same as t. So I can pull this out and it will just become t on the outside. So it's t cubed. And this would be 9t squared plus 4. So we want to actually integrate this. Now we do have a couple situations where we can actually do this. For one, we can actually do a trig sub, right? So like 3t equals 2 tangent theta. But remember, whenever you want to do a trig sub, you ask yourself seriously, do I really need to do this? Because that's going to kind of be annoying. But here, the t on the factor of t that I have on the outside is actually a t to an odd power, which means a regular substitution could work. So that's what I'm actually going to do. So as before, to not have to worry about the radical, I'm going to set u squared equals what's underneath that radical. Now, of course, that's going to have certain consequences. For example, if I were to take t squared, that's going to be u squared minus 4 all over 9. And I'm also going to change the limits. When t equals 0, our u would be 2. When t equals 1, our u would be rad 13 of all things. Okay, but let's actually follow through with the substitution. So this means 2u du is equal to 18t dt. And so what I can do here is just actually replace this thing. To get 18 to be 2, I'm going to divide by 9, multiply by pi. This means 2 pi over 9u du is going to replace my 2 pi t dt. So by the way, this is going to be the integral from 0 to 1, 2 pi times t squared times t times the radical of 9t squared plus 4 dt. And I'm going to replace this. We'll replace that. So I would have 2 pi u over 9 du. This is from 2 up to rad 13. So that is replacing this part, the 2 pi t dt. Okay, cool. Then I'm going to replace the t squared, which is this guy here, with u squared minus 4 over 9. Awesome. Then I can replace this whole thing based on this whole thing. So that's just going to be u. All right, so now my integral from 2 to rad 13, that's going to be 2 pi over 81 times u to the 4th minus 4u squared. So actually, I can actually start just integrating right away. So this is 2 pi over 81 times u to the 5th over 5 minus 4u cubed over 3 between 2 and radical 13. So this is going to be 2 pi over 81 times 13 to the 5 over 2 over 5 minus 32 over 3. No, I'm gonna plug in the radical 13. 4 times 13 to the 3 over 2 over 3 minus 32 over 5 plus 32 over 3. All right, so this is going to be 2 pi over 81. I can actually put all this over 15. So I can get 3 times 13 to the 5 over 2 minus 20 times 13 to the 3 over 2. Here I'd have minus 3 times 32 plus 5 times 32. That's 2 times 32. Okay, so that's going to be 64 all over 15. And that's for that one. Looked like a pretty innocent curve, but that was a lot of integration. But that's that will be the surface area. Cubic units. So we have that at a glance. Okay. Another example. Last example of the semester. Very excited. Can you tell how excited I am? Very excited. Okay. Oh, this curve, same thing. We're rotating around the x-axis. Rotating around the y-axis just means I put in the x here instead of the y. So I would have put in this formula instead of this formula. Would have actually made things, in this case, would have actually made things worse. At that point, I would have had to do a trig sub. Like I couldn't really escape it. But yeah, putting in the y here was nicer. So here's another one. This is really what we're doing, just an exercise in integration. So here, using s equals, we're going around the x-axis. Applying this formula. This gives us that our s is going to be the integral from 1 to 3 of 2 pi times 8 rad t times the radical. The derivative of x is 4t, and I want to square that. No, x has 2 terms, so it's going to be a bunch of things squared. So it's going to be 4t minus 1 over t squared plus the derivative of y is going to be four t to the minus 1/2 squared dt. Right, because I write radical t as t to the 1/2, differentiate that, the half comes down, divides into the 8, you get 4, subtract 1 from the power, you get minus 1/2. So we have this. So now we're going to figure out how to I would actually start to expand this here. So this would be like 16 t squared. This times 2. So you'd have 8 over t plus that squared, 1 over t to the 4th. Plus here you would have 16 over t. So I can simplify that. This is 16 pi rad t times the radical of 16t squared. This will be plus 8 over t plus 1 over t to the 4th dt. Okay, so notice if I compare this to this, which comes from that, I can realize that what I'm looking at is actually a square. It just looks like the top thing all squared, but with a plus in the middle. For t plus 1 over t squared dt. Now, of course, that's going to come out as like 4t plus 1 over t squared dt. There's going to be, technically speaking, absolute values here. Would that affect anything? No, t goes from 1 to 3. That's going to be positive the whole time. So I can actually ignore the absolute values. So I'm going to take a t to the half. I'm going to multiply in. That's 4t to the 3/2 plus, that's t to the minus 2 plus 1/2 t to the minus 3/2. So it's going to be 16 pi times, add 1 to the power, divide by the new power. And this one, you add 1 to the power, divide by the new power. So you have that. So now you go in, you plug in the 3. Minus plug in the 1. Simplify this a little bit. I can take a 2 outside. This would be 4 over 5 times 3 to the 5 over 2. Minus, let's wrap 3 over 3. Minus 8 over 5. Plus 2 over plus 2. Well, 3 to the 5 halves is actually 9 times rad 3. And the 2 I can think of as 10 over 5. So this I can actually simplify to 2 over 5. Let's put these all over 15 again. So 4 times 9. And I'm going to multiply that by 3. So that's like 12 times 9. So this is 108 rad 3 minus 5 rad 3 plus 6. I feel I don't. I read this out a while back. I don't think that's the answer. That was my mistake. Oh, I actually didn't. Okay, so I factored out a 2 here. But technically this is 4 and 1. Oh, so this would be a 1 over 5. This would be a 3. Yeah, I think that looks right. Yeah, and that is the last example. So we are done. Mic drop. Not going to drop my pencil because this, I don't know for sure, but I'm sure it's going to be expensive to replace. But that's it. That's the end of Calculus 2. Welcome. You guys survived. Okay, that's it. So, I mean, last day, relatively easy stuff, I think. It's just knowing these formulas and applying them. It's an exercise in integration. Essentially, you know the formulas. So with this, you can, we finished the syllabus, including stuff that, I didn't really even care if we finished it or not. But yeah, we finished the complete syllabus, including all these 3 topics that were optional in my head. We also finished those. So yeah, we are done. Well, almost. We're done with the lecture material. So just to remind you, test 2 is currently open. It's due tomorrow by 9. Homework has been extended, and now you know everything to complete the homework. It's extended to Saturday at some point. I think Saturday at midnight. Well, technically, I think it's like Saturday at 2 a.m. I don't know why the clock changes it to 2 a.m., but I would say just get it done by midnight. Finals on Monday during regular class time. Other than that, it's just study and finish up all the homework and stuff. So, yeah. With that, I will just kind of end the day asking if you guys have any questions about anything, about what we did today, or anything you want to ask that you encountered on practice test 2 that you kind of want to go over before you try test 2, assuming you haven't tried test 2. I don't know how many people actually did the test already, but yeah. So I will pause here for questions. But the moment we are done with questions, we can actually sign off. Looks like 3 people have taken test 2 already. So I think for the rest of you, yeah, the final is everything. So, so the final is going to be pretty much a combination of test 1 and test 2 plus everything below this line. Well, below here. So this also need to know for the final. So if you go over everything that we did, go over the first 2 tests, go over all the practice tests, go over all the homework, just go over everything, because I'm sure even if you did a bunch of practice for test 1, probably forgot some of that stuff right now. I wasn't going to open it at 3 p.m. I was gonna we were gonna do it during regular class time. No, the final would be actually longer. So the standard time period of the final is about 2 hours, but being everything is online, you guys have to like upload work and stuff. So it'll probably be 2.5 hours long. So final covers everything. It's cumulative. So practice everything. And it'll be on Monday at 6, roughly 2.5 hours long. So instead of class, we'll have the final, essentially. It replaces the class. Any other questions? General questions about like how we're going to wrap up. So the final is Monday. The goal is to have everything graded by and all the grades out by Wednesday, included in the real homework grades. But like I said, the report card I sent you after test 1, it assumed that your homework grade was 100%. So which means, if you're basing it off of that, you want to kind of keep your homework grade at 100%, which means your overall homework grade needs to be at least 90%. And after Saturday, so on Sunday, I'll like collect all the homework grades, and at that point. But you should be able to see your progress on the homework and know what your grade is going to be. Just try to make it over 90%, and I'll give you the last 10% for free. Homework is due Saturday. Test 2 is due by tomorrow at 9 p.m. final is Monday. I mean, should I be writing this all down? Let me write this in the notes. So you have it in like me verbally saying it and final announcements. Test 2 due tomorrow, Friday, August 5th at 9 p.m. That's the first thing. Homework due Saturday, Saturday, August 6th at midnight. Final is cumulative on Monday, August 8th during regular class time. We'll send more instructions via email. So just be on the lookout. I think that's roughly it. So it's going to be roughly 2 hours, 30 minutes. So you log in here, I administer the final, and by 8:30 you're out. And at that point, the final will be the last thing I have to grade. So I'll probably try to finish grading by Tuesday, let you guys know your grades by then. And by end of day Wednesday is when I want to like input the grades officially. Any other questions? Any questions on things from the practice test for test 2 or problems that you want to do?
Just a general question. Will we know
Yeah.
our grade for the second exam before the final?
Yeah. So it's like last time. I think last time I sent out the grades on Sunday. It'll be like the same thing. So it'll be due on Friday. I'll grade it Saturday. I'll send out the grades on Sunday. Or you'll see it updated by Sunday in Blackboard.
Cool. Thank you.
Mm-hmm. Other questions? All right. If there are no more questions right now, questions later, you of course email me, follow the instructions on the exam, and I'm gonna let you all go for now. So if you want to go finish up the test or go study a little bit more for the test, take it tomorrow, that is fine. Either way, we are kind of signing off now for the final time. Good luck on your exams, guys. Have a great rest of summer and have great future semesters. But yeah, I bid you all adieu. See you guys on Monday. Ciao.